All right, let's get started again. This is second talk in a mini course I'm making on spectral graph theory. And so last time I introduced the main player, the graph Laplacian, and I explained a little bit about how we could think of it as being a sort of discrete replacement of the Laplace operator. In this talk, I'll talk mostly about some examples and some results that seem to be given perhaps first in Anderson and Morley, but I wouldn't be surprised if the results I'm going to show today are known in earlier sources that just aren't known. Who knows? I'm not a historian. Anyway, so get to it. The path graph. So path graph is what it sounds like. We have 1, 2, 3, and 4, and 5, all the way out to n nodes, or vertices if you like, each connected by an edge, except for the last one and the first one. So the first and the last are a little bit different, and correspondingly the Laplace matrix here has the first and the last column a little bit different than all the ones in the middle. All the ones in the middle have 3 non-zero entries. They've got a minus c, a 2c, and a minus c corresponding to, well, the second column, right? 1 goes to 2, 2 goes to 3. That gives me the minus c and the minus c from subtracting the adjacency matrix, of course, and then the 2c in the middle, because there's this one and that one both going into 2, giving us that 2c. And so forth. So that's what the Laplace matrix looks like here for the path graph. And then I just want to look at the n equals 4 case, dig down into that a little bit more, do some calculations here. So the Laplace matrix looks like this for n equals 4. And I went ahead and I used MATLAB to calculate the spectrum of L. So I use the Eig command. Eig, if you say a pair equal to Eig, it gives you back 2 matrices. The one matrix will have the eigenvectors, supposing they exist, I suppose. I actually don't know what this does when the matrix is not diagonalizable, but anyway, this one is, since it's a real symmetric matrix, it is orthonormally diagonalizable, meaning that you can look at its eigenbasis. In fact, here's the eigenbasis right here, these put into a set. And you can scale them to have length 1. These are all unit vectors. And they're pairwise perpendicular, right? They're orthogonal. And so if you look at this matrix A, it's actually an element of O4, the orthogonal group. But then the B, the output of Eig, gives you the eigenvalues in the diagonal. And this is pretty neat because this means that we can take L and we can actually rewrite it as the product of A, B, A transpose like that, which is a close cousin to the diagonalization of L, which you could get from multiplying this on both sides by A transpose, because A transpose A is I. So we get the A transpose LA is equal to B, and B is a diagonal matrix. This is how we diagonalize L. Now, of course, as we are going to be looking at formulas for the graph Laplacian in the upcoming videos, this will become important because, you know, if we can choose eigencoordinates, that means the formula for the graph Laplacian is sort of in its most simple form in some sense. But more on that later. Let's just look at the spectrum here. We have 0, we have 0.58, 2.00, and 3.4142 according to the precision of my computer. MATLAB 2019B, I think. And interesting things to notice, we only have 0 once. The multiplicity of 0 is just 0, is not 0, but it's 1. And then the eigenvalues, the largest eigenvalue here, 3.41242, is less than 4. And I think that's something we'll see as we look at different graphs. Now, to be careful, so I think if we look at a graph on n vertices, I think we're going to see that the eigenvalue, the largest eigenvalue is less than n. In fact, I think that's part of a theorem I'm going to prove here a little bit later. But that probably does assume that the weights are 1. So we'll keep an eye out for that. We can also look at the path graph on five things, and I haven't drawn the picture, but I did go ahead and do the calculation since it takes not too much more time. Certainly took me much more time to type it into MATLAB than it did for my computer to do it. And the spectrum for the 5-path graph is this. 1, 0 eigenvalue, 0.38, 1.38, 2.62, 3.62 roughly. So again, the largest eigenvalue is less than 5. And also, again, one of the things you might start to pick up on is that the vector 1, 1, 1, 1, 1, or in the previous, the n equals 4, 1, 1, 1, 1. Sometimes they'll call it the constant vector in the literature here. That vector is going to be in the null space of the matrix. So when you multiply it by the matrix by that 1, 1, 1 vector, it's going to give you back 0. And there's a significance to that we'll be trying to understand as we go on. All right, now, next example. Oh, actually, excuse me. Sorry. I had more to say here. I forgot. It's been like a whole couple hours since I wrote these notes. I should not forget these things, right? Okay, so n equals 4. It's kind of interesting. So what this picture is I'm looking at the 4 nodes, and I'm graphing the eigenvector in the vertical sense above or below the node, just to try to like visualize it. And so the 0 eigenvector, because the MATLAB normalizes the length 1 rather than doing 1, 1, 1, 1, it's minus 0.5, minus 0.5, minus 0.5, minus 0.5, because the length of that vector is 1. So I graphed that here as these green dots. And I just took the liberty of connecting the solid dots by dotted lines so you can kind of see what's going on better. So that's the first eigenvalue, and the corresponding sort of, I guess you could say, function, let's say. And then for eigenvalue 0.5858, you've got this plus, plus, minus, minus pattern, which I've taken liberty of trying to graph in here. So up here, then a little bit lower, then the same but negative, and then a little bit in. So I may have failed to actually draw these. I'm trying to draw these correctly, but I'm sorry if I haven't done justice. 0.5 above and 0.5 below being the same. My bad. I hope you can see the pattern now. Eigenvalue 2, we get plus, minus, minus, plus, which kind of looks like this. It drops down, and then goes back up again. And then finally, the highest eigenvalue, 3.4142, we get minus, plus kind of pattern. And so I've made that one black, so it starts below, it goes above, it goes down, it goes back up. Again, just plotting the magnitude of the eigenvector above or below the corresponding node. And I think you can really start to see different, if you think about this as being like a sort of silly discretization of a string as 4 points that are strung together, you can start to see, the string is just like that, or it's got, sort of this kind of wave in it, or it's got and these more and more complicated possible motions, discretization of motions of a string. Something like that's going on here. And there's a very, very noticeable pattern in these path graph eigenvectors if you go on. So like I didn't want to write them out. But if you get out your handy dandy MATLAB or Octave perhaps, whatever, and you calculate the spectrum for the path graph on 5 vertices, you'll again get this nice pluses and minus patterns. Like the lowest eigenvalue 0 has the constant vector as its eigenvector, and then the next lowest eigenvalue 0.38, it crosses 0 once, minus minus goes through 0, plus plus, and the next one up crosses through 0 twice, above, below, 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 above again. And let's see here, the next to last eigenvalue crosses 0 1, 2, 3 times, and then finally the highest eigenvalue, 3.618 in the n equals 5 case, it goes plus minus plus minus. So we get 1, 2, 3, 4 crossings, four zero crossings if we look at that. So sort of the higher eigenvalues are corresponding to more excited modes in the discretization, if you want to think of it that way. All right, let's go on here. Like I said, the greater the value of lambda for a given Laplacian, the more sign changes the corresponding elements of the eigenvectors take on. And the lambda equal to 0 eigenvector is constant. So I wanted to look I'm trying to build up enough examples here so that as we go on in this talk and the ones upcoming, we'll be able to appreciate what the theorems are saying. So I think having a good set of examples is as important as understanding proofs of theorems, if not more. I'm sure some people would argue more. Most of those people are students. All right, so here, number 8, page 8 rather. I made up this graph. So I've got this 1, 2, 3 connected, and 4 and 5 connected. And I took the liberty of making the weights on the 1, 2, 3 to be C, and the weights on 4 and 5 to be 2C. So the adjacency matrix looks like this. As you can see, 1 is connected to 2 and 3, 2 is connected to 1 and 3, 3 is connected to 1 and 2, but not 4 and 5, and on the other hand, 4 and 5 are connected, but not to anything else. So that gets us this adjacency matrix, which gives us this Laplacian. These are zeros. I don't know if you could see it or not, but they're zeros there. I wrote them in white. I wrote them in purple down here. So here's the Laplace matrix, assuming that the constant C is 1, right? That still has a weight 2 over there. Great. And I then point out that some calculations you don't need MATLAB for, right? You should be able to see that if we look at 1, 1, 1, 0, 0, think about taking that, think of this as a column vector, right? So just in case you don't know already, when I write this, that is a shorthand for, I'll just write it again. 1, 1, 1, 0, 0 is my notation for the column vector. If I want a row vector, I would write it with square brackets. So that's a distinction in my notation. And mostly because I don't want to write column vectors in the middle of paragraphs of text. And so to be fair and to make that equals not a ridiculous comment, I put a transpose here. There we go. All right. Or if you really love MATLAB, you put a prime there, but it just seems wrong. Anyway. Okay, so this is an eigenvector with eigenvalue 0. That is an eigenvector with eigenvalue 0, right? Because if you look at multiplying that times this, 0, 0, 0, and then 2 minus 2, 2 minus 2 plus 2, zeros all around. So eigenvalue 1 and eigenvalue 2, they're both 0. All right, we're going to go with the nomenclature that we number the eigenvalues from 1 to n. There will always be n real eigenvalues because we're dealing with a symmetric matrix. Now, I used MATLAB to calculate the rest of the spectrum, and I went ahead and looked up this thing called the characteristic polynomial, and it gives you back, if you do char poly L, it gives you back 1, minus 10, 33, minus 36, 0, 0. And, you know, I'm just doing this to illustrate some of the underlying mathematics. Of course, if you're just after the spectrum, you don't need to do that. You can just go straight to the Eigen command, right? But I wanted to understand what I did wrong in another page I'm not showing you, where I tried to calculate this directly and was again reminded that 3 by 3 matrices are easy to calculate the determinant of in principle, but much harder in practice. And anyway, so this means that the characteristic polynomial is x to the 5th minus 10x to the 4th plus 33x cubed minus 36x squared plus 0x plus 0. These are the coefficients of the characteristic polynomial, which is defined to be the determinant of x minus the Laplacian here. So if you look, you can factor out an x squared, which is good because that shows you that we have root 0 twice for the characteristic polynomial, which corresponds to these two eigenvectors. The geometric multiplicity given by the existence of these is equal to the algebraic multiplicity, as shown by that x squared there. And then you've got this thing, which obviously you can factor as x minus 3 squared times x minus 4, right? No, that's not obvious, but, you know, I also calculated the, the spectrum, so I knew that there was a 3 repeated in a 4. So there it is. And in fact, using Eig, wait for it, come on, here we go, scooch that up a bit. So as I mentioned, those are the 0 eigenvectors. The eigenvectors for eigenvalue 3 are this guy and that guy. Notice they're both corresponding to those 1, 2, 3 nodes which are connected together, and then this corresponds to that 4, 5 part of the graph which was connected together. So the number of sign changes is, you know, not particularly, there's not much I can say about that. It's not like the 4 eigenvalue has more sign changes than the 3 eigenvalue, right? For what it's worth. And I also don't get to say that the largest eigenvalue is larger than the number of things in the graph, which was 5 here. I think when we use non-unity weights, we could manufacture an eigenvalue which was larger than the number of vertices, but I don't know if I actually have that example in the set of examples I'm going to show in this video, so maybe I'll get back to that in a future video. Okay, moving on. So one of the other popular examples to look at is the complete graph. Actually, this was the complete graph on 3 things. G is K3, and then the complement to a graph is the graph with the same vertex set, but all of the edges which were not present in the original graph are present in the other graph, but all of the possible edges between 3 things are already here. So the complementary graph to the complete graph is just the silly graph which is vertices with no edges. Great. And for what it's worth, here's the spectrum of both of those. So I can rip off the spectrum from our calculations in the previous one, where I learned that that block gave us eigenvalues 0 and 3 2 times, and ignoring the zeros on the 4, 5 part, I get these 3 vectors, right? So I'm just to put it here. So like you see, this gives you that, this gives that one, this gives that one. I just approximated them because I got tired of writing 4 decimal places. So there's the eigenbasis for the complete graph on 3 things. And then the complementary graph is the 0 Laplacian, which has just eigenvalue 0, 3 repeated, and literally any choice of 3 linearly independent vectors is an eigenbasis. It's very silly. All right, so just to state the definition carefully for future reference, I suppose. Given a set of vertices V and edges E, the graph G, which we can write as V comma E. I haven't been doing this up to this point, but a graph is always a vertex set and an edge set. It's a pair. Well, the complementary graph, G bar, is the same vertex set, but with the complementary edge set. And the complementary edge set, E bar, is defined by E and E bar, if and only if E is not an E. All right, and I can tell you a little theorem. If the cardinality, if the number of vertices is n, and G is a graph with edge set E, then you can form the complete graph by taking the vertex set and just using the edges in the graph and also the edges in the complementary graph. That gives you all your edges, which gives you the complete graph. All right. So what about the spectrum of the complete graph? Well, let's look at that. The complete graph, I was so foolish as to draw the complete graph on 8 vertices. There you go. It's actually a lot of, you start drawing these, you could, it's a lot of fun. You could try to do it for 20. It would keep you busy for a while. Maybe that's a good punishment for a misbehaving child in this time of quarantine. I don't know. They might like it though, I don't know. Oh well. Anyway, stupidity aside, this is the Laplace matrix for Kn, and if you tilt your head and squint at this for a while, you'll see what you really have is n on the diagonals, and then a matrix with all -1s everywhere. So you could rewrite it as n times the identity minus k, or as I would like to refer to this in the future, the Nick formula. And so anyway, again, notice that you have the 1, 1, 1, 1, 1, 1 vector as a null vector. It has eigenvalue 0. And I'm using lambda 1 equal to 0 because it's our custom in here to write eigenvalues from least to greatest. I will warn you, some of the papers that I've looked at, they have the spectrum enumerated the opposite way, so that the 0 eigenvalues are at the end, but you know, this is what we're going to do. Now, by symmetry here, I think you can calculate the spectrum of this graph by symmetry. And what I mean by that is that if you look at this, there's a symmetry between all the nodes, right? They're all equal in the sense that no one is special. Each one has the same like number of edges. You know, if you could imagine yourself living on the graph and being on one of these points, you wouldn't be able to tell if you were at 2 or 3 or 4 or 5 unless you could look down and see the 2, 3, 4, 5, right? If you just tried to judge it on the basis of edges emanating from the node, you couldn't tell where you were. There's a symmetry amongst the nodes. And so it stands to reason, since we don't have all 0 eigenvalues, because that would imply that the Laplace graph is the Laplace is the 0 matrix, which is not. It must be that the non-zero eigenvalues that remain are all the same. So by symmetry, I argue that. And so, in fact, the trace, a little bit of linear algebra for you here, the trace is the sum of the eigenvalues, right? And so that would be lambda 1 plus n minus 1 times lambda, right? Because lambda 2 and lambda 3, they're all lambda, so there's n minus 1 of them, so n minus 1 times lambda. Of course, that lambda 1 is just 0. And we can also calculate the trace directly, right? The trace is the sum of the diagonals. So you've got n minus 1 plus n minus 1 plus dot 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 plus n minus 1, n-fold times, right? So n times n minus 1. This is 0. And so you look at it, you divide by n minus 1, we find that lambda equals to n. So the eigenvalues for the complete graph are 0 or n, where n is repeated n minus 1 fold times. There's an n minus 1 fold degeneracy on the complete graph. Now, I'm pretty yeah, this is in the paper by Anderson and Morley, but I think I discovered this example myself a few weeks ago, just fooling around. And so I think other people may have found it if they. This is a natural thing to look at. Now, there's a bit of theory here about symmetric matrices which we should appreciate and try to use and exploit. That theory is as follows. If you have two, given a symmetric matrix, if we have distinct eigenvalues, lambda I and lambda j, then the eigenspaces corresponding to I and jth eigenvalue, they're perpendicular. What that means is that if you take any vector from here and any vector from there and you take their dot product, they're 0. Right? So like the xy plane and the z-axis or something like that. All right. And in the case there are just two distinct eigenvalues overall, that means that the direct sum decomposition is the whole space again. And but it's more than that. It's an orthogonal decomposition. Like these are perpendicular subspaces in the sense that the perpendicular to the for my example, for the complete graph example, the perpendicular to the 0 subspace is the n subspace, and the perpendicular to the n subspace is the 0 subspace. All right. And more than that, I had a moment of thinking, and I realized, oh, the lambda equals n eigenvectors are just perpendicular to the 0 eigenvector, right? Because of this theorem, which means it's pretty easy to see what they are. You got to think of what's perpendicular to the 1, 1, 1, 1, 1, 1, 1 vector. Well, you just take 1 minus 1, right? Then the dot product of this with the 1, 1, 1, 1 vector will be 0, and or this, or all the way on out to that. They're n minus 1 of these. These are the eigenvectors with eigenvalue n. I didn't need to calculate it directly. I could just kind of guess it. All right. Of course, for a given n, you're welcome to use the Eigen command in MATLAB, as we will. Next example, the ring or cycle graph here. So here I'll look at the one with 4 vertices. And so we have 1, 2, 3, 4. I chose the weights to be all 1. It's just like the path with 4, just like the path graph with 4. All that's different is we added in these guys right here. This minus 1 and minus 1 corresponds to the connecting of 1 and 4. So if you just kind of erase that and just string out 1, 2, 3, 4, then you're back to the path graph, right? So they're kind of related in that sense. Once more, we see that this is the eigenvector with eigenvalue 0. If ABCD is an eigenvector of L, I was feeling guilty for using MATLAB so much, so I decided to calculate one by hand. Well, that's not the only reason. I'll confess the source of my calculations here in just a second. But anyway, if we have ABCD, a vector which is perpendicular to the 0 eigenspace, all right, then that would be the sort of thing that we're looking for if we want to look for a non-zero eigenvector. That's what I'm doing. I'm looking for a non-zero eigenvector, so that means it has to be perpendicular to the 0 eigenvector, which is super handy because that gives me a plus b plus c plus d equal to 0. Now, so we face this equation. If we look at the eigenvector problem directly, there's your matrix L times the eigenvector equals lambda times the eigenvector. So if you look at that and just look at the equations, we get these equations, all right? So like 2a and the lambda, bring the a terms to the same side, I get 2 minus a lambda. This gives me the b, that gives me the d, so b plus d. Similar story for the other rows. So we get these 4 equations. Then if you add these, add the first 2 or add the last 2, notice that you get a plus b plus c plus d in both. And so you get 2 minus lambda times a plus b equal to 0, or 2 minus lambda times c plus d equal to 0, which are easier to think about because the only way we can have a product of two things be 0 is if either that's 0 or that's 0, right? So from 1, we find that either lambda equals to 2 equals 0 or a plus b equal to 0. I suppose it's also possible they could both be 0, but anyway, it won't concern us. We can find what we need from this. So for example, if lambda equals to 2, then calculations, which I'm not going to show you, indicate that 1, 0, minus 1, 0, and 0, 1, 0, minus 1 are eigenvectors with eigenvalue 2. It's easy enough to take these and check them. If you multiply by that, you'll get twice that. Multiply this by that, you get twice that again, eigenvalue 2. The other possibility, a plus b equal to 0, also forces c plus d equal to 0. And so lambda equals to 4, it ends up happening there, and you get this vector 1 minus 1, 1 minus 1. Again, if you take that up here, you can easily see that you get the vector 4 minus 4, 4 minus 4 from multiplying this on that, which corresponds to the fact that that's an eigenvector with eigenvalue 4. Now, so let's see here. So it's a nice example. Let's just talk about what we have here. We've got for eigenvalue 0, this vector, eigenvalue 2, these guys, for eigenvalue 4, those guys, right? So again, we see the sign change thing, right? No sign change, 1 sign change, and then 1, 2, 3 sign changes for eigenvalue 4. And in fact, that's part of that observation we were making before. Now, if you want to calculate the spectrum of the ring or cycle graph for arbitrary n, it can be shown that the spectrum is 2 times 1 minus cosine of 2 pi k over n, or if you prefer, you could do 4 sine squared pi k over n, where k equals to 1, 2, da 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 n. and the so like the eigenvalue 0 has multiplicity 1 here, and the next non-zero eigenvalue has multiplicity 2, I believe. You can read more about the spectrum of the Ringer cycle graph and other things other than Anderson and Morley, but this is from Anderson and Morley, page 145 of Anderson and Morley. Actually, I still haven't admitted where I got this calculation from, but I will shortly. What about the complement of the cycle, 4 cycle? So if I don't connect 1 and 2, or 3 and 4, or 2 and 3, or 1 and 4 like that, then what's not connected directly here? Well, 1 and 3, and 2 and 4, right? So the complement of C4 is this guy. So this graph is disconnected. You could rewrite this as 1 connects to 3, 2 connects to 4 if you were so inclined. And this gives us this graph Laplacian for the complement, which got, lots of zeros. And anyway, it's easy to see that 1, 0, 1 and 0, 1, 0, 1. So this is corresponding to 1, 3. This is corresponding to 2, 4. These are eigenvectors with eigenvalue 0. And you can also kind of just eyeball it and see that, well, again, using my intuition guided by theory, the other eigenvalues, non-zero eigenvalues, must give vectors which are perpendicular to the 0 eigenvalues, right? So if I find vectors perpendicular to that, like this, and if I find a vector perpendicular to that, like this, then those should be eigenvectors, probably. And in fact, they are. This, you can calculate, gives you 2v3. This gives you 2v4. So in fact, we have eigenvalue 2 with multiplicity 2. All right. Now, so that's kind of a neat example. And then one more example here on this page. Let's see here. And so, in fact, the last example before this and this one were inspired in part by this lovely set of notes by Rachel Quinlan, School of Mathematics, Statistics, and Applied Mathematics, NUI Galway, 2017. I'm not actually sure where this is. I don't feel like it's in the US. I'm not sure where that is, but I found it. In fact, I was happy to find this because the first PDF I found of this, which I've been working with for a few weeks, doesn't have the author or the source. So I just got this chapter 3. Like, what's this from? I don't know. Well, I figured it out. It's from this. And here's the web address, maths.nuigalwai.ie / R. Quinlan teaching. I'll try to include this link in the comments for this video because these are great notes, which partly inspire this talk here. But anyway, for the star on n vertices, so here's the star on 8 vertices, all right? This gives Laplacian like that. So you've got the 1 is special, right? It's connected to all of the others. And then the other ones are just connected to the 1. So it's kind of nice. And we have 0 eigenvalue once, corresponding to that eigenvector. We have the 8 eigenvalue once, corresponding to that eigenvector. And I won't try to describe what the eigenvectors are in between, but there is some regular pattern that can be found there. Maybe we'll come back to that in a future talk, but there you go. This is the spectrum for the star graph. It looks like this. Again, notice that the largest eigenvalue for this weight 1 graph is not larger than the number of vertices. And the eigenvalue 0 for this connected graph was just multiplicity 1. In contrast, the eigenvalue 0 here was multiplicity 2, and this graph was not connected. So we're starting to generate some circumstantial evidence for the following theorem. All right. And so here it is. This is the big theorem for today. If the graph G has n vertices and lambda is an eigenvalue of the graph Laplacian, then 0 is less than lambda is less than n. Now I should mention, I've forgotten to write here, but this is a, writing in yellow never works well. I'll try green, maybe if the weight 1. weight 1. I'm pretty sure it has to be weight 1. So if the weight 1 graph has n vertices and lambda is an eigenvalue, then the eigenvalue has to be between 0 and n. The multiplicity of 0 equals to the number of components, that means connected components of G, and the multiplicity of lambda equal to n is 1 less than the number of components of the complementary graph. The formal publication date is 1985 in Linear Algebra and Multilinear Algebra Journal, but there's a footnote which mentions that this was actually a widely circulated technical report originating in 1971. Apparently, University of Maryland Technical Report, TR-71-45, October 71. All right, so let's get to the proof. Now, so we'll start out with the, this is actually going to rely on some of the things we did last time. The main result we need from last time is that the graph Laplacian can be written as the product of the edge or incidence matrix and its transpose. That's actually mission critical here for this argument. So suppose you got an eigenvector, let it have length 1, that's my pointer, length 1, and eigenvalue lambda. So it's length 1, the dot product of x with itself is 1, and then that says that we can do this. We can say lambda is equal to that, right? But lambda x is Lx, and remember L is E transpose for some edge matrix, incidence matrix, like so. And second, I want to keep us focused here. I need to. This is a double blind proof. How appropriate. You always want your proofs to be double blind. All right, now that dot product is the same as taking the transpose of the vector times the vector, right? How to rewrite the dot product as a matrix product, that's how you do it. Then the sock-shoes property, the transpose of the product is the product of the transposes in opposite order. Is where I get this x transpose, E transpose, transpose, E transpose. Of course, this by sock-shoes again can be rewritten as E transpose x transpose times E transpose x. And then, well, hooray, that's the dot product of E transpose x with E transpose x, which is to say that it's the length of E transpose times x squared. Now that's really, really nice because that says that the eigenvalue is equal to the squared length of a vector, which means that the eigenvalue is non-negative. All right, so that means this matrix is positive semi-definite or semi. Oh, I forget the. I'll get back to that. Proper name calling here eventually, but anyway, the eigenvalues are non-negative. We can't have a negative eigenvalue. It's pretty nice. So the spectrum of L is non-negative. Next, we're going to let V1, and I'm just following the proof in Anderson and Morley just directly here, guys. So let V1 through Vk be vertices of a connected component of G. Then the sum of the corresponding rows of E is 0, and any k minus 1 of these rows are independent. It follows that the nullity of E, and hence E transpose, is equal to the number of components of G. So I read this, and they looked like words that made sense, but then I was like, what? Why? So I thought it would be helpful to actually give a sort of example with some meat to it to try to digest this paragraph. And so if we have this disconnected graph, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, this component and that component and that component, they're disconnected, right? And here's the incidence matrix over here. So he's claiming the sum of corresponding rows of E is 0. So what does that mean? Well, the corresponding rows for 1, 2, 3, 4, 1 are these, right? And if you think about adding these, you get 0, right? Because you always have the minus 1 and 1 corresponding to the edge, which is connected in any of the edge columns. And it's also clear that if you take out any one of these rows, you'd still have independent, right? Like, it doesn't matter which one you delete, you have the remaining 3 are independent, right? So that goes to show that that there are k minus 1 linearly independent rows. We know that there aren't k, because if we add all 4 of them together, we get 0, which is a linear dependence, right? And likewise for the other components, right? Like if you add the 5, 6, and 7 together, you get 0. If you add 8 and 9 together, you get 0. And there are at most 3 independent vectors that can be chosen from there, at most 2 from there, at most 1 from there. But more to the point, I would point out that if you look at 1, 1, 1, 0, 0, 0, or 1's in the middle but 0's on the outside, or 1's at the end and 0's before, then this corresponding to that, that corresponding to that, that corresponding to that, these are null vectors they're going to be null vectors for E transpose. And I invite you to check that. If you take the transpose of this matrix and you multiply it by that, or that, or that, you'll get 0. And that implies that this, or this are also null vectors of the Laplacian, which means that the nullity of the Laplacian is in fact 3, which is also the number of components, which goes to show you that, you know, the argument is correct. Now this, you know, it's important that the k minus rows are independent. That keeps the nullity from rising past 3, right? Each one of these blocks gives you a null vector. You can't have more additional null vectors from here, because if you did, it would correspond. It would contradict the linear independence which we observed by deleting rows. There is something there to think about, but I don't know. I think the proof is legitimate. Don't be wrong. It's just, you know, proofs are written for an audience, and you know, sometimes you have to work a little bit to fill in the gap. Now, so continuing, if, because what else is there to prove in this theorem? It says that the eigenvalues are between 0 and n, and it talks about relating the multiplicity of the 0 eigenvalue to the number of components of G, and the multiplicity of the n eigenvalue n to the number of components of the complement, right? So let's see how that goes. So interestingly, the proof is based on the fact that the graph and its complement are related to the complete graph. And so, really neat argument. We know that the 1, 1, 1, 1 vector is a null vector for the graph, the complement, and the complete graph, right? So if we think about any other eigenvector which is perpendicular to 1, 1, 1, 1, right? Then what can we say about that? Now, in principle, if we had more eigenvectors with eigenvalue 0 to go around, it could be that x is an eigenvector with eigenvalue 0 again, right? You could have two if the 0 space is more than one dimensional. It's possible to have another vector in addition to this which is perpendicular to that in the 0 space itself. But that's not possible here because the complete graph has spectrum 0 and n. Remember the n minus 1 multiplicity of the n eigenvalue for the complete graph, which means if x is an eigenvector and, right, it's not the 1, 1, 1, 1. It's not, so, you know, x is not the 1, 1, 1, 1 vector. We know the 1, 1, 1 vector has eigenvalue 0 for kn. That means that x must have eigenvalue n for kn by our previous work. All right, so what does that mean? Well, that means we can calculate the what happens when we take the Laplacian of the complement to the graph acting on x. Remember, this is equal to that minus that by this calculation right up here. Oops, that's yellow. But anyway, that gives you, I wonder if you can even see that. I can barely see it. Anyway, so that minus that, but remember, this times that gives me nx, that times that gives me lambda x by assumption, and so we get n minus lambda times x, which means that x is both an eigenvector for the graph Laplacian, but also its opposite, right? Which is kind of neat. I wonder what that means, that the eigenvectors are shared between the graph and its complement. But in any event, So still the graph Laplacian for the complement is a graph Laplacian, which means the original part of this argument still applies. It's a symmetric matrix. It has to have non-negative eigenvalues, which means that n minus lambda has to be greater than or equal to 0. But that's just what we're looking for, because that means that n is greater than or equal to lambda, which means that we have 0 less than or equal to lambda less than or equal to n. Yay. And furthermore, by the calculation above, if that's the spectrum, if lambda 1 through lambda n is the spectrum from LG, then n minus lambda 1, n minus lambda, n minus 1, n minus lambda 2, n minus lambda 1 is the spectrum for the complement. So this is how the spectrum of LG and the spectrum of the complement are related. Furthermore, we can, kind of look at that and go, okay, so if we had n, multiplicity of n for the original graph would be the same as the multiplicity of n minus lambda for the complementary graph, right? But that's 0. And remember that the number of times 0 is repeated is the number of connected components in G bar. And the multiplicity of 0 is the same as the multiplicity of n. So thus the multiplicity of the eigenvalue n for the complementary graphs gives the number of connected components for G. And there's all kinds of other sort of neat little things you can say about connecting the spectrum of the graph and its complementary graph. But here's a corollary to the theorem. If G has n vertices, then n is an eigenvalue for the graph Laplacian, then G is connected. Because if you go through it, you can get a contradiction using the theorem, basically, that if the condition above in G was not connected, then G bar would be connected. And that would mean that you have x such that LGx equaled nx, but also 1, 1, 1, 1 would be null to LG bar. So that would say that the nullity of LG bar was, larger than 1, which would imply that the number of components is more than 1, which is to say that G bar is not connected, which contradicts, of course, the assumption that G bar is connected. Hence, by proof by contradiction, the corollary holds. Anyway, so that's kind of a neat test. If you see that your eigenvalue n for a weight 1 graph is present, then that means G is connected. All right, so we're starting to accumulate some results about the connectivity of a graph as it relates to the eigenvalues, and hopefully we'll be able to dig further into that as we go on and study the other papers. So I'm going to stop there for now. Thanks, guys.